Welcome everyone to my talk TSDB another year in. So in the last PromCon which happened in November 2019, I gave a similar talk called TSDB 1 year in where I talked about what went into the TSDB since the Prometheus 2.0 release. And in this talk I'm going to talk what went into the TSDB since we had the last PromCon which was in November 2019. So little about myself. I'm a software engineer at Grafana Labs and I'm a Prometheus member and I maintain the time series database part of the Prometheus. And I'll be sharing these slides after the talk, so make sure you follow me on Twitter. I'll be sharing it there. So let's see what happened in TSDB since PromCon 2019. The outline of this talk is going to be, first we start with what went into TSDB already which are available in the Prometheus releases, and we will move on to what's coming up, and we'll end with the features that were added for the downstream users like Cortex, Thanos, etc. So what's already in? Isolation. So isolation is finally in. I talked about this even in the last PromCon. So the basic idea about this is, earlier if you had like 1000 metrics that you were scraping and you use that in a histogram query, and if the scrape is complete only up to like 500 metrics, and if you query the TSDB, you could see partial results like 500 metrics of the new scrape, 500 metrics from the old scrape. So this creates problems in various scenarios and isolation fixes it. So this work was started by Brian long ago, and in the last PromCon I mentioned Gautam took it forward, but that went stale again. Finally Beyond, who is one of the earliest member of Prometheus, took the charge and finally finished the work which Brian and Gautam had started, and isolation is finally in. So if you are querying, you won't see partial scrape. So how this is implemented is, we assign something called appender ID for every append that comes into the TSDB, and using this append ID, when we query, we have an isolation state. When we are iterating through the samples during the query, we see if the append ID that the sample corresponds to, whether it's an active query, like the active append which is not committed yet, then we discard it. So with some logic around that, we have achieved the isolation. Now the next thing. So I'm going to talk about a series of optimizations which Brian put in the 2.15 release. So in the bottom right corner of every slide, I have the release number mentioned in which these optimizations are there. For example, isolation had 2.17, so isolation is there since the release 2.17. Now let's talk about these optimizations. So in the couple of optimizations that I'm going to talk about, Brian reduced the memory footprint that a loaded block takes, and both have some similar ideas. In the slide that you're seeing right now, a posting is offset in the index where the series information is stored. So when I tell a posting, it actually refers to a series, and for every label value pair, we have a list of postings that they appear in, like the list of series that they appear in, and that list is stored somewhere again in the index, and the offset where it's stored is called posting offset. So for every label value pair that exists, we were storing that in memory along with its offset. So in this optimization, what Brian did was, we don't actually need to store all those offsets. We can store only like nth offset. In this case, we are storing every 30-second offset. So whenever you want to get the posting offset, like the posting list offset, you can just binary search through this nth position, and when you are satisfied it falls in a certain bucket, then you can iterate through those 32 items. This reduce the memory footprint taken by this offset table in the memory by about 98%, which was great. And another thing was the symbols. So symbols take up a lot of memory if you have lots of series, and again, symbols are just strings which appear in the series label and value. So they are sorted and stored on the disk. So we need not store all the symbols in the memory. So in this optimization, what Brian did was we again store every nth symbol. I guess it's again every 30-second symbol, and the symbols that are used throughout the index are via offsets. For example, we store the symbols only once in the index, and we use the offset at where it's stored in other places so that we can save space. So whenever you want to look at some symbol, you can just binary search through this nth symbol and then iterate inside that bucket to find your symbol. So this actually reduced the memory footprint by a huge amount, obviously with performance penalty on querying side, but this optimization pays off when you have larger installations. And these are some set of optimizations that were performed on compaction. I'm not going in detail about these optimizations, else it will take up the entire time. The main idea behind this was whenever you're compacting and writing the data into the disk, mainly the index, you need not store all the data in the memory while you are in the compaction process. What you could do is when you are at somewhere in mid process, you could read back some data which you have already written in the index and do some calculations over that so that you can write the further data. Basically, the whole idea of all these optimizations is don't store it in the memory, reread it from the disk whenever possible. This makes the compaction slower, obviously, but it's a background process, so it's fine. But it actually makes the compaction process constant memory. And all these block memory optimizations and the compaction optimizations came into 2.15. So if you are on versions before that, you could see some spikes in memory happening when there is a compaction, and even when you have more and more blocks, maybe your heap size is gradually increasing. But if you shift to any version above 2.15, then you should see there are no longer any spikes during compaction, and the memory footprint stays almost constant because the head memory grows and comes back, grows and comes back. So that's a nice thing upgrading to 2.15 or newer versions. Now another very simple optimization but very powerful, this reduces the write head log replay time. Before version 2.18, we used to store like 6 hours of write ahead log, which is totally unnecessary, and nobody took a look, I guess, for a very long time that we are doing this. And one day Brian just comes up saying, hey, we are storing a lot of wall and we don't need to keep around so much wall. And if you see the simple change here, we have like multiplying the amount of wall to delete by 1 by 3. So just make it 2 by 3, like double the amount of wall you delete. This doesn't cause any data loss because the way the truncation of write head log works. But if your system is disk IO bound, then it can make the replays actually, like the restarts, actually 50% faster. So this was a very nice optimization which came in version 2.18. So let's move on to another interesting optimization which came in version 2.19, which is memory mapping of chunks. So the samples in the head block or even the disk, so head block is the in-memory block and the samples are stored in something called chunks. 120 samples comprises of one chunk. So whenever a chunk is full, like 120 samples, we cut another chunk. So if you have like 15-second scrape interval, it can turn out to be like 6 chunks per series in memory because head stores up to 3 hours of data. So in this optimization, what we do is once a chunk is full, for example 120 samples, we just write it to the disk and store the reference of that chunk on the disk into the memory. So the entire chunk is replaced by a single reference. And whenever you want to read this chunk, you use the feature given by the OS, which is memory mapping, which fetches the chunk from the disk on demand whenever you need it. So if you don't query a lot on your head block, this means earlier we were storing 6 chunks per series in the memory. Now you will effectively store up to 1 chunk per series in the memory. So in real world, this turns out to be like 20 to 40% reduction in the heap size. And as a side effect of this, because you are already have stored the chunk on the disk, when you're replaying the write-ahead log, you can discard a lot of samples because the chunk is already memory mapped on the disk. And this makes the write-ahead log replay like 20 to 30% faster. So for every release, we run something called PromBench to benchmark previous release with the current release. And these are some graphs uh, showing the memory benefits of this memory mapping work. So this is for a very high churn. When I say churn, it means the rate at which new memory series are being created or they disappear. So in high churn scenario, we have like 10 to 20% reduction in memory. But if you look at low churn scenarios, which might be most of the cases, I guess, there is 30 to 40% reduction in heap. And if you look closely, this green line is actually the heap size of the memory mapping and not the lines above it. So that's pretty good. So this was all about, these were the main highlights of the optimizations and the features that went into TSDB since last PromCon. It's like less than a year, but there are still lots of optimization that went in. Now let's talk about the future, what you can expect in the coming releases. So this is another optimization following the memory mapping work, which is snapshotting of the chunks that are there in the memory to speed up the replay process. So this idea came from the write-ahead log work which was being done in the Cortex project, and I did an experiment on this last year in the November sometime. But because there was no memory mapping work in existence, that would cause a lot of write amplification because we had to snapshot all the data that's in the memory to the disk. Now that we have memory mapping, what we could do is I said we store one chunk per memory series in the memory. So whenever you are shutting down the Prometheus, you can take the snapshot of that last chunk for every series along with the series label values and the tombstones and flush it to the disk. So whenever you are restarting Prometheus, it can read the series and the in-memory data from the snapshot, and it can iterate through the memory map chunk to restore the references, and that's all you need to do. You don't need to go through the write-ahead log again. This makes the restart time up to 80% faster or even more from the current test that we have done. So the PR is already up with a proof of concept implementation. That PR just needs a little more work and a lot of testing before it can be merged. And I actually expect it to go out in the next release, which is 2.20 as a best case. But in the worst case, I hope it will be in by the release 2.21. So yep, you can expect faster restarts in the upcoming releases. That's great. And this is a very long-standing feature request and a long-standing PR. So there were lots of reviews on this PR. Lots of iterations have been done to solve some of the critical issues that can happen with data import, like a large block size, memory explosion, other problems. But the only thing that it's blocked on is what format to support in this tool, like what should be the format to input data into the Prometheus. So Bartek, who is another maintainer, ran a Twitter poll where the remote write format actually won in terms of poll, but this PR implements open metrics format. So there is still requirement for some discussions upon which format to use, and maybe we'll also support multiple formats, who knows. And after that is fixed, the PR just needs a little more review and the tool should be in, like the first version of the tool. Obviously some optimizations will follow this, but a tool for bulk import of data into Prometheus is somewhere around the corner. And about lifting the index size limit, so this work has been standing for over an year, I guess. This was done in GSOC 2019. So as I said before, postings are the offset in the index where the data of the series is stored. Currently the postings are 32 bits which are 16 byte aligned. With that I mean, if you take a posting of 32 bit, the actual offset in the index is that 32-bit number multiplied by 16, and series are always 16 byte aligned on the disk too. So with this, with 32 bits and 16 byte alignment, the index size limit is capped at 64 gigabytes, and some installations can cross this, and there is no way you can have a larger index size than 64 GB right now. One of the solution is to move to 64-bit postings, but it comes with the problems in its own. One of the problem is space on the disk. Like if you are just doubling the number of bits that you store for posting, it's going to take a lot of space on disk. And not just that, when you are storing a lot of data on disk, fetching it is also slower. And one of the thing Prometheus aims is query performance. So when the move to 64-bit postings come, you have to take care of both performance and the space. So we tried and tested lots of different compressions that we can do on this 64-bit postings, and after lots of testing we decided to go with prefix compression, where you store a common prefix and a list of suffixes and call it a bucket. In 64-bit postings we chose 48 bits of prefix and 16 bits of the suffix, which gives near equal performance of 32-bit postings, and they actually take less space than what we're taking right now. So the PR just needs a little more review, and because there have not been many requests for this feature, it has kind of gotten stale, but after some review it should be good to go in. So let's end with what were the features that were added for downstream users, which is not actually accessible in the Prometheus binary itself. So there's just one feature that I'm going to talk about, which is callbacks for series lifecycle. So these are just set of three methods that you can pass into TSDB when you are creating an instance of it, with which you can create how many series that you want to be created. So there are methods like pre-creation, post-creation, post-deletion. In pre-creation you can keep a count of series or any metric that you want to keep a track of, and you can return an error if you don't want that particular series to be created. For example, Cortex already uses it and has a per user limit, so it keeps track of a series per user, and it has a per metric limit. For example, for a given metric name, how many series you want to create. So this can be done using these three callbacks. So if you are a consumer of TSDB package, you can write your own custom methods to take care of the series creation. Yep, and that's about it that I had, and thank you for joining my talk. I think you can now ask questions in the live chat, or if there's something else, please reach out to me. In case you have any questions to ask later, this is my Twitter handle _Codsum, so you can just DM me anytime. Thank you. So the first question is, with mmap, will it lead to spikes in read latency because the OS might have decided to flush the page to the disk, etc. So in practice, even when we're running benchmarks on the prom bench, we haven't seen any latencies as such. Running the queries is similar to how you'd run queries on the persistent block where the chunks are mmapped, but this is all assuming fast SSDs, and in practice you won't see any latencies really. And the next question is, are there any plans to improve histograms in TSDB? I think yes, we have Beyond, who is actively working on improving histograms on TSDB. So yes, there are plans and the work is ongoing. Have you considered alternative chunk encoding in TSDB? Yes, that's also in one of the roadmaps or the plans to consider alternative chunk encoding based on the data that you see. So the answer to that question is yes, we are considering, and that might be something that might qualify Prometheus to release 3.0. Who knows?
there was an interesting discussion going on the Slack channel about mmap and syscalls. Do you want to talk about that at all?
It's similar to the first question that was asked, whether there will be spike in the read latencies because of disk write and read colliding. So the answer is same. In practice, we haven't seen any issues like that. And for assuming you are running this on a fast SSD, there won't be any issues or performance impact with the mapping. Yes.
Looks like we have one more question in the Q&A.
Yes. Why 3 hours of write log? A block is cut on disk every 2 hours. So we don't truncate write-ahead log exactly with the time in mind. And previously it was 6 hours of write-ahead log. The basic logic what we follow is, if there are X segments of write-ahead log on the disk, we truncate 2/3 of those segments and we don't actually take care of time. And also 3 hours because the data that's there in the head block is up to 3 hours and not 2 hours. Because whenever the data in the head touches 3 hours, we cut the old 2 hours of data into a block and there is still 1 hour of data in the head. So looking in that perspective, because head stores data for up to 3 hours, the write-ahead log needs to be there for 3 hours. Any plans of allowing values to bytes of arbitrary lengths? It would open up so many interesting challenges for performance. I don't think that's actually in the roadmap and not something we are considering right now. It would be a fixed value length. So the next question is about, is there any regression between 2.15 to 2.16 release where there is a 40% increase in bytes per sample? So I can't really answer this question right now. I would have to look at the release. So maybe this discussion can be taken offline. I think there is an issue open already talking about this, but there is no regression, known regression. But yeah, this discussion has to be taken offline, I guess. Are there plans to rewrite TSDBs from scratch? I don't think so. Like, it took a very long time to get the TSDB in Prometheus 2.0 right, with lots of races and lots of issues initially. So I don't think writing it from the scratch is in the plans.
All right. Actually, I had one. Have you put any thought into supporting uint64 as an additional data type in addition to the float64 that we currently support?
I haven't thought in that direction at all, changing the data type of the value that we store. But it would be interesting to see possibilities with that in terms of compression or any other thing. But before that, maybe we want to consider different types of chunk encoding, and maybe later we can jump to different type of data types. We have a question in the group chat. Yeah, I mentioned in one of the Slack discussion in CNCF that TSDB is not really meant to use with the write-ahead log. And the question is why? I think, as far as I have understood, working with the TSDB, we assume Prometheus will use the write-ahead log, and the implementation inside the TSDB code is based on the assumption that there will be write-ahead log when you're running this in a scene setup or in Prometheus. And the case of no write-ahead log is only for writing unit tests. So that's the reason the TSDB should be used with the write-ahead log, because not much has been checked or tested when there is no write-ahead log. But I think you can still run with write-ahead log, but not in a Prometheus binary. It's not allowed.
We have another question in the Q&A.
Oh, yeah. Any plans to introduce more caching in PromCore, similar to Cortex query frontend? I don't think any discussion around the caching has been done for Prometheus, but I think if it's feasible, we might introduce caching, or I think Cortex query frontend itself is very easy to use. You can just place it in front of the Prometheus and have the caching layer. So I guess the answer is no, because you have a solution already, but if it looks very interesting, it might be merged into Prometheus. But in near-term future, I guess that's a no.
Yeah, there's several different caching front ends, including the Cortex query, and then Trickster is also a good caching front end. All right, thanks a lot, Ganesh.